Hello, hello. Bear with me. Slight. Hello. There's Colin. There's Brandon.
Hello. Good morning.
And there's the voice. Or good morning. Yes, good morning. Thank you both. Hold on. More. Okay, I'm doing things out of order for small change. There's Brittany. There was Brittany. There's Brittany. All right. We got Colin. We got Brandon. We got Brittany. We got Judith. We got Xavier. We got like a full house, which does not beat a straight flush, but comes up more frequently. Good morning, Shaynell. Good morning, Gaia. Good morning, Ryan. Good morning, Ariana. Good morning, Brittany, the double. Good morning, Charlene. Good morning, Adenelsi. Edmund. Good, good morning, Anissa. Who else? Okay, bear with and avatars. Good morning, Ariana. Good morning, Anissa. Good morning, Charlene, the double. Good morning, Emily. Who else did I say? Xavier, Judith, Brittany, Brandon, Colin. Awesome. And the avatar on the MP, the military police. No, the Maria, I believe. All right, hold on. The board's coming in. The board is coming in. Is the board coming in? Hang on, bear with. And good morning, Emily, if I didn't say, and good morning, Carolina, if I didn't say, I didn't say. Okay, hold. Okay, bear with me another. Uh, I see that. I hear that some. Wait, stupid technical or technological question. When somebody, I'm asking any of you or all of you, when somebody enters the waiting room and it beeps on my side, does it beep to you guys as like, can you tell what? Yes. Okay. Thank you. And thank you, Brandon. That is points right there. That was a fast response. Thank you. Okay. So like, that this is, so that's good. Just in case I space. Oh, and that was a yes from Colin. Thank you, Colin. I appreciate it. And Brandon. And again, I know it sounds silly, but feel free to submit for points for that because like it helps everybody. And good morning, Maria. Okay. All right. Oh, and there's two of me. That is the last thing that anybody needs, including my wife. Hold on a second. Nobody needs two of me. How do we? Okay. Right. Okay. All right. Bear with me first. So now we're pretty much ready. It's 10:53. We have a slightly packed agenda today, so I should not be wasting any more time. Um, but I will. So bear with me for a second. Okay. All right. I'm going to, so I think you can see from the board sort of, or you can infer from the board that my agenda today is to briefly and momentarily recap where we've gotten to so far with Galileo's principle of relativity. Huge concept, like super important concept. I want to recap where we got into with that, expand a little bit further, and then reassure you that that is never going away. Galileo's principle of relativity underlies all of physics, as far as I'm concerned, as far as I'm concerned, and I don't think I'm the only one who feels that way. Um, so we're going to do a little more with it today, But then we're going to shift gears and get back to sort of going over the homework, which I know like you're way ahead of me right now, and that's terrific. You're way ahead of me, a lot of you. And I have to catch up with you. And that also does mean, and I'm aware of that. So if I need to readjust the next homework deadline, I might well do that. Like I am watching. And that will happen if I need to give us more time to catch up with ourselves. So just be aware that I'm aware. But so we're going to recap and move a little further with Galileo's principle of relativity right now. Then we're going to start, explicitly going over homework 4 and being more mathy and problem solving again. But I want you to know before I do that A, this is not the end of Galileo's principle of relativity at all, by any means. B, it will, even if it ever feels a little disjointed, that sometimes we're talking about this sort of conceptual aspect of physics, and then sometimes we're like cranking through mathematical looking problem solving. I want you to know that in the end, it's all related. And you'll see more and more as you progress through this class or the next one. The more you see how the concepts and the math are related, the better you'll be doing for sure. And in particular, the more you see how anything we ever say conceptually about Galileo's principle of relativity, the more you see how that whenever stuck in solving a physics problem, whenever a physics problem seems challenging or confusing, and you're like stuck trying to solve it, my first recommendation is back up to steps 1, 2, and 3 more than people tend to do. Like, don't think about step 4 of solving a problem until you really explicitly lay out steps 1 and 2. And then which means really know what the problem really, try to put the problem in your own words and in your own drawing before you jump to like, I don't know how to solve this. It's really important to make sure that you know what you're being asked. But then once you've done that, steps 1 and 2, when you're thinking about step 3, like what do I really need to solve this problem? People tend to think that what they're searching for is equation. Well, people tend to think that what they're searching for is formulas. I'm here to say, first of all, get rid of the idea of formulas from your mind and start thinking in terms of equations. And there is a subtle distinction. But second of all, when you're thinking of equations, first think in English. Yes, by the end of the day, once you're solving a problem, you need to be able to capture whatever the operative thoughts are. You need to be able to capture them in symbols with constants and variables and mathematical operations such as trigonometry or calculus or whatever. But none of us do. Well, you don't, especially when you're stuck, don't jump to the symbolic ways of writing things down. Don't think, what equation did I forget to memorize for this or whatever. Think conceptually and try to draw the equations out of the concepts. And if there's one concept to go to, especially when you think you've run out of concepts or when you're stuck, I'm here to pledge to you that if there's one concept that's sort of always there and always important, but often overlooked or forgotten, it is Galileo's principle of relativity. So I'm going to go back to what that means in a second, but I'm basically saying short story long. I'm saying whenever it seems like we're just talking about concepts in this class, we're just talking about English. I mean, for some of you, that's more enjoyable, like obviously. And for others of you, it's frustrating because like you just want to get to the problems. I know that. But what I'm here to say is whenever we're talking about concepts or English, what we're really doing is trying to help you really, really improve your ability to come up with something to say for step 3, GDP, general definitions and principles, whenever you're stuck solving a hard problem. And that is physics 203 and physics 204 and like whatever, modern, 20th century post-Einstein physics. When in doubt, the concept that's super important and is Galileo's principle of relativity. Okay, so I'm just looking at the chat. So We're going to talk a little, and that's the concept that comes out of this whole train of thought experiment, which really is just a way of thinking about all the deep thought we've all gone through throughout history regarding what the heck is going on Earth in relation to the universe. Sorry. Okay. So to recap, all right. So Galileo's principle of relativity, and I'm going to change the view on the screen. So every time I say, if nothing else, if you want to memorize things, like every time I say GPR, I mean Galileo's principle of relativity. And every time I say Galileo's principle of relativity, if nothing else, intuitively, what you should think in your mind, at least at this stage, what you should think of is the reason that we're able to believe, or the reason that we're able to even entertain the possibility that Earth might be hurtling past the sun at 65,000 miles per hour all the time, and yet none of us ever feel it, see it, sense it. Well, I shouldn't say see it, but that none of us ever have any sensory evidence that we can go through our lives feeling like we're walking around on a stable floor whilst believing that that floor is moving past the sun at 65,000 miles an hour. The idea, which that paradox, and you should regard it as a paradox, the idea that one part of our brain is like la-di-da, I'm walking from here to there and not worrying about anything, and the other part of our brain is like, oh yes, I'm on a rock that's going through space at 65,000 miles an hour. Like the fact that somehow our brain could be comfortable with both of those views at the same time is resolved by this notion called Galileo's principle of relativity, okay, which is said many different ways, and we're going to say it many different ways in this course, and is a principle. It's a principle, which means it's even deeper than a law. It's the principle, it's the fuel in the machine that generates the laws of physics. Like, seriously, it comes before. Right? That's what, notice in this course, we're already a month and a half into this course. We have some equations, we have some definitions, we have some, like, we're doing stuff. We don't have a freaking law yet. Like, literally, we do not have a law. And that is because before we can even establish laws, we have to establish what the nature of those laws governing space, time, and motion would be. So the principle. The first way it can be said, so this part is review, technically. I'm just reviewing what I said last time, but then I'm going to move on. Form number one of Galileo's principle of relativity is the laws of physics, like whatever they are, whatever they're going to be, 10 years from now, 100 years from now, 1,000 years from now, unless someone changes this principle, the laws of physics are the same in all. Okay, so someone is here. I know that. Oh, wait, hold on a second. Okay, hold on. I know someone's here. Okay. And again, notice every time I write, I'm telling you that we're going to say this in different ways. I mean, manifestly different ways. But even every time, so in other words, there's going to be a form number 2 in like a minute, and a form number 3. Different ways of looking at ultimately the same fundamental idea. But even when I write each form, you will notice I'm going to write each form slightly different words each time. That's not an accident. Like, the original thing wasn't written in English anyway. So each time I'm going to use slightly different English words depending on like how sophisticated I think your language has gotten to be by this point. So one of the more proper ways to write this form, right, is what I wrote right here. The laws of physics are whatever they are, And again, this is assuming we don't even know them yet. Like literally, Galileo came up with this before Newton even came up with Newton's first law or Newton's second law or Newton's third law of motion or whatever. So the laws of physics, whatever they're going to be, are are the same in all inertial reference frames. Okay, now we're going to have to expand on that, like in a way for the rest of our lives. But quick, if you're taking notes about anything, not just what I write, if you're writing down things that I don't write down, I would suggest, which I suggest you do, I would suggest that you note that inertial, what it really means is unaccelerated. Like really, that's what it means. Inertial means unaccelerated. So same speed, same direction. Okay, and reference frame, oh, if you're going to write it down, and we definitely, a reference frame is a perspective maintained, or a perspective and or coordinate system. I mean, okay, perspective is the English way of putting a coordinate system, is a more quantitative way of putting it, but okay, in physics they have to be the same thing. I mean, there's no perspective in physics that isn't a coordinate system, but so perspective or coordinate system maintained by an observer who regards themselves as at rest, like an observer who regards itself as at rest, as stationary. I'm going to say that one more time. A reference frame is a perspective or coordinate system maintained, used by an observer regarding itself as at rest, as stationary, as standing still. Okay, that's what a reference frame is. So it's a perspective on the world. It's a measuring system, but it's one where whoever's holding it treats themselves as stationary and treats everything else as moving by them. Okay, so in short, what this form of this principle says is, so the short version of, I mean, it's sort of more, if that's too much verbiage for you at the moment, or like too many ideas packed in one at the moment, which I understand, then the fast way of saying what I'm saying is that Galileo's principle says the laws of physics, whatever they are going to be the same at all different constant velocities. Doesn't matter if you're going 100 miles an hour to the north or 3,000 miles an hour to the southeast. Like once you fix a speed and direction and you look at the world from that perspective, whatever the laws are to you are the same as to anybody else who is also looking at the world, but from some other different constant speed or constant direction. Okay, that is the principle, and I'm sure that's the principle. And Galileo, this is like, really quickly, sort of what the anchor of this principle, I mean, no pun intended, well, pun totally intended. The anchor of this principle is that when people came to Galileo, people or colleagues or people of major authority or people who were holding the purse strings to his research, when people said, dude, what? The Earth, you're saying the Earth could be moving at like 65,000 miles an hour? Like, dude, it does not feel like the Earth is moving at all. And I don't care what that can of yours with little like dots of light in it seems to say to you. Like, look at the floor, it ain't moving. And if I drop a book while I'm standing in my library, the book lands directly below my hand on the floor, like next to my feet, right? The book doesn't land behind me, as I believe it would if I were like dropping it from, like a moving vessel. They would say this. The book like lands directly below my hand. So how can you possibly say, Galileo? And it even is true if I even drop the book outside. It's not like because my house is doing something special. If I drop something, it lands on the ground below my hand, which is what happens when things are standing still. So how can you say that the Earth is not standing still, Galileo? And again, I want to emphasize that's a very legitimate question, right? I mean, it's not just like sort of a reasonable question. It's like a powerful, important question. Like if it can't be answered, then either our notion of Earth or our notion of motion is like totally messed up or not really useful, right? So what does Galileo say? What Galileo says, and he doesn't just say it, like he writes it in, wonderful books that are satirical and clever and obnoxious and subtle and have tons of drawings in them. Galileo says, yo, 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 wait, hold on. Everything you just said is true. Like if you drop a book, like or drop a whatever, it lands at your feet. Yes, that's like all true. He's like, but hang on. Imagine, and literally, I'm not, this is like in a book called in a book called Dialogue on Two Chief Systems of the World. Um, he says, guys, picture yourself in a boat. Like we have boats. It's the year 1632. We have boats. Picture yourself going down to the bottom of a boat and like doing a bunch of it while the boat is parked, while the boat is anchored. Picture yourself going down to the bottom of the boat while it's anchored, go to like the captain's whatever quarters and like do anything you want. Like do a bunch, observe a bunch of things. Look at the desk in the captain's quarters, how stable it is. Look at a bowl, literally look at a fish bowl on the desk with a fish like nicely swimming around in the bowl. Apparently they had that then. Who knew? And like drop a ball down there or play freaking, racquetball off the walls if you want. And like notice what it's all like. Do any experiments and observations you like while the ship is anchored. Then let the ship set sail in a smooth way, in a comparatively reasonably smooth way, even though nothing is like perfectly smooth on the ocean by any means, but let the boat sort of cruise more or less smoothly on the ocean waters and go while it's cruising. You see where this is going. While the boat is sailing, reasonably, under reasonably smooth, constant velocity conditions, go back downstairs to the captain's quarters and do all your observations again and check out the fish in the bowl and drop something on the floor. And don't you notice they're all the freaking same? That's what he doesn't say freaking, right? And he doesn't yell like, oh, he probably does yell sometimes. But his point is, if you're on a ship, whether the ship is anchored or the ship is cruising, every observation and measurement you make is going to work out the same, i.e., the laws of physics don't change when you're sitting there versus when you're moving. That's this principle right here. He's saying, you already know this, whoever you are, from ships and boats. You know the laws don't. That's why you're willing to go on a boat and maybe not even get seasick, some of you, right? Like why a boat is okay. And in modern terms, this is all, you substitute airplane, and it's a much more dramatic example. Like some of us go on airplanes and somehow are okay on airplane rides, and not just okay, like we complain about the food they're serving as though that's the priority. You know what I'm saying? Like we treat airplane rides like they're hotel rooms. And Galileo says, you guys treat ships like they're hotel rooms. How could you do that unless the laws of physics were the same no matter what speed you're going? And furthermore, Galileo is really saying not only must the laws be the same, whether you at any constant velocity, but you must all already know that. Like this isn't even new. We must already all tacitly agree to this. That's why he's calling it a principle, not even a law. It's not even a new discovery. It's a new recognition of the importance of old knowledge, which is really how physics works. He's saying, dudes, you already agree with this. You conduct your life as though you already agree that the laws of physics are the same at all constant velocities. Does that prove that the Earth definitely is moving? No, but it does mean that any argument against the Earth's motion is not really a good argument. That's what he's saying, right? So in fact, wait, I'm just looking at the chat. Okay, hold on, I'm switching the board. So that's the principle. The principle is the laws are the same, whether you're going 100 miles an hour to the north or 3,000 miles an hour to the northeast. The laws, whatever they are the same. Therefore, I'm just switching the screen. Okay. Therefore, I'm now going to give you, now we're going to move on. That's form 1. Here's form 2. Now, please, people get this. I'm saying this is now, I'm going to say a different, I'm going to look at that same idea from a different perspective, like a different intellectual perspective. So this is what I'm about to write. Please hear this. In fact, I'm just going to say, just because people get this confused all the time, and I think it's just raise your electronic hand if you like hear me speaking emphatically right now. Just like raise your hand if you're with me. Awesome. That's a lot. That's 8. That's great. Thank you. I can't even see the names, but that's at least 11, 12, 13. Great. Good enough for me. Thank you. I appreciate it. And you can all give yourself points for that and a pat on the back and a cookie. Because what I'm saying is, I'm about to write form number two of GPR. It's still GPR. It is not a different law. It's not a law. It's not a different principle. It's a different form of the principle. And just to caution you, every next chapter we ever do in Physics 203, every next idea, even when it looks like we're changing topics, is just another form of the same principle. We're going to get a total of 9 of these forms, not all today. But so, okay, so I'm saying each new form is like, and that's what happened in history in a way. Like each new big discovery or way of doing physics is, in my judgment and in my, according to my research, is just like a new extension or expansion or logical inference from another one of these prior forms. So we're just, physics is just a pushing all the implications we can squeeze out of this fundamental idea that the earth could move and we could not feel it. Okay, so each new thing. So on an exam, don't write GPR number two or something. Like this is GPR form number two is eh, okay. Form number two is the implication of form number one. And essentially, I've been like saying this in examples that I just was yelling about, but now here's the explicit statement of it. So and again, by the way, when I say form number one, form number two, I mean these are different ways that Galileo emphasized or used the ideas in different chapters of certain books or of different books. Like these are okay. So I'm not saying he laid them out like there's no like table of contents, form one, form two. But these are different implications that come up that now can be retroactively organized this way. So form number two says, given form number one, if the laws are the same, if the laws are the same at all constant velocities, then that means you cannot do an experiment. Like you literally cannot even design an experiment that would enable you to measure how fast and in what direction something is going in and of itself. When I say absolute, I don't mean by absolute, that's what I mean. I mean in and of itself, as in not compared to anything else, as in relative to space itself. So what I'm saying is this, and this is like again, this is very important. And in a way, again, by the way, and this is the way physics works, I think that I'm saying things that you all most of you have like known your whole lives, just didn't necessarily know that they were important or always true or as true as you thought, or that you were allowed to think of these as like scientific truths, right? But I think you know this, which is, and that's the way it's supposed to be. We're trying to say things that we think everybody would agree with, but that we can then use in big ways. So what this is saying is, look. In the train of thought experiment, or like you wake up in an airplane in the middle of the night, and you're like, wait, are we there yet? Are we there yet? And then like, and it feels all smooth, so you can't really tell, like, or have we even taken off? Did I fall asleep before we even took off? Like, what's going on? And then, excuse me. So you're like, I don't even know if we're moving or not, right? And then let's even say you look out the window, and let's say you see clouds moving past the window, right? So you're like, oh, there's clouds moving. But then you're like, wait, okay, I see clouds moving past the window, but hang on. Clearly there's like motion of some kind, but are the clouds moving past me while I'm actually still? Or, which maybe is weird if you're on the ground, but you get the point. Or are the clouds still while I'm actually moving past the clouds, right? Like legitimate question. Or if you don't like the airplane example, I'm sure you can come up with other examples. Or, on the highway when you're in traffic and there's like a huge tractor trailer next to you, and there's that moment where it's like, oh, did I just release my foot off the brake and I'm sliding forward? Or oh no, the truck is going backward. And when you're trying to resolve in your mind what's actually going on, Galileo's saying there ain't no actually, comma, yo, there ain't no actually about it. Like, really, on a deep scientific level, Galileo's saying, hang on, what can be said is like that there's motion sort of between the truck and you. But, but as far as who's actually moving, like in and of itself, compared to just like empty space, not compared to some other object, that cannot be tested in an experiment at all. Not for lack of technology, but because if we really believe form number one, if we really believe the laws are the same no matter how fast you're going, well, then that means experiments are always going to result in the same result no matter how fast you're going, whether you're actually going 100 miles an hour or actually sitting still, the laws will be the same. So the experiment will necessarily have the same finding, the same result. In other words, the whole thing of like, if you're in the ship and you're like, is the ship actually moving yet? Are we cruising or are we still at port? So then you like, do something you like are in your room and you're like, I'll do an experiment because I'm a scientist. Or not even just because I'm like a rational person. So you like so you're like, I'm gonna drop something next to me in my room in this ship. And you say to yourself the very reasonable thing of like, I know that if I were standing still, whatever I would drop would land directly below my hand because I experientially already know something about gravity, just like people have for 300 years. I don't know the equations. I haven't like I'm not like a high level technological gravity experimenter, but like I know things fall down in straight lines when I'm standing still. So I say to myself, I'm going to drop something. And if it falls in a straight line and lands at my feet, then I guess I'm standing still. But Galileo says, no, you can't do that. I mean, you can do whatever you want. But the fact is, even if you weren't standing still, if you were going 100 miles an hour at a constant direction, the laws would still be the same. So the freaking thing would still land directly below your hand. So you can't do an experiment to find out whether you're actually going past something else or it is actually going past you. You literally can, I mean, this is very, okay, you see the extension. Form number one is the laws are the same, whatever they are. And if you're like anybody else, you're like, why is everybody screaming all the time? Like, duh, the laws are the same. Like, of course. I mean, if they're laws, wouldn't they be the same? Yeah, yeah. We're trying to say, like, yeah, that should be hard to argue that the laws of motion, the laws that govern speed, velocity, acceleration, whatever they are going to be, like they shouldn't change from speed to speed. Just like municipal laws don't change from criminal to criminal. Like you know what I'm saying? Like that's what makes them laws, right? So the first form, we should all just be like, yeah, I get it. I just don't get why it's a big deal. But then Galileo says, well, it is kind of a big deal because if you get form number one, then form number two says, I don't care how advanced your equipment is, you cannot design an experiment to find out whether you're actually sitting still, you're actually moving, or what actual speed you're going. If by actually you mean you by yourself, not compared to anything, just compared to space. So when this says, and I'm going to move on now, I think, when this says you can't do an experiment to measure the velocity of a single object, I don't mean you can't make any measurements ever at all. And I don't mean you can't talk about velocity, like all of physics. This is all happening. We can't because all of physics is ultimately about motion. So we're laying down the ground rules of motion right now. We're not saying you can never measure motion, but we are saying what you can't measure is the motion of one object. Like literally, like one object by itself does not have, we're saying you cannot design an experiment to measure its speed just like by itself or compared to space. You cannot do it because form number one says the laws are always the same. So form number two says, so you can't do an experiment. Now then comes form number three. Now stop me, obviously, if I'm yelling. Oh, wow. I was just about to say stop me, but someone did. Hold on. Yes, thank you, direct chat person who I totally want to, yay. And I'm not going to say your name out of respect, comma, yo, because you went in the direct chat. Yeah. No, you're gaining. All right, so someone's in the direct. Quick sidebar? Someone's in the direct chat, totally rocking this and like getting it, saying that they're losing brain cells. I think they're gaining brain cells. But I totally get why they're in the direct chat because they're not sure. But like, wait, oh, okay, I'm gonna say please let this be a lesson to everybody. And the person whose name might or might not be Charlene, is rocking it right now. And I'm not trying to single her out or unsingle the rest of you out. But I want to say, like, she should totally submit for points right now. Charlene should submit for like 85,000 points. It's not an application. You get the points. You just have to remind, whatever. She should totally get 1,000,000 points right now because she's rocking in the direct chat. And believe me, I totally get why people use the direct chat. And that's what's good about Zoom, that you can do that. But hopefully you guys will get more. You're totally going to pass the class. Yes, you're rocking the class. Right. More and more part of what remember, guys, physics is just code for group therapy for math trauma healing. Like I'm joking, obviously, but not really, right? Like what I'm hoping is that by the end of this semester or next semester, and those of you who keep rocking in the direct chat will feel more and more comfortable to come out in public and rock because it will help everybody. Because again, one thing to remember, and I know, but I get it right now. It's fine if you're in the direct chat. Like there's 1,000 reasons that you're worried about your peers and this and that. And let's be honest, one thing some of you might be concerned about is that you don't want your peers to know that you're rocking because then that makes them nervous because it's like a competition. And then they're like hating on the rocker and all that stuff. But I do have to remind you, and I will get back to material in a second, but it is important. Like we're trying to all get to be smarter, better scientists and get jobs and all that stuff. And let me remind you that even if the world is dog eat dog, it's less so than you think. And it's less so when you make it less so. And this class is not. We are not. Remember, I don't have a limited number of A's to record into CUNY first. That's an important thing. That doesn't mean I'm a nice guy. It means it affects your strategy. Charlene can get an A without it jeopardizing the A of A. I'm not saying she's definitely going to get an A, but I'm saying any inch that Charlene makes toward an A does not threaten anybody else's A. And in fact, the more confidently we believe that, the more Charlene will help other people or whoever it is. Obviously, I'm just making a big thing, but like you all can help each other get more A's, not less. That's really important to know, to understand, which is another reason to just go for it and get in the public chat when you want, because then whatever, then we can all feel like it's a class and it's not just about a crazy man in the front of the room yelling electronically. Okay, but anyway, so no, oh my God, wait, I did not say you might not get, you might not, I don't know. I'm just saying it's not a, oh my God. All right, oh, now she's going with the voice.
Because that was shade.
I don't even know what that means, but now I do. All right, okay.
It's like when you're low-key being disrespectful.
Oh my God, no, I'm totally, this
No, I'm
is,
playing. Chill.
oh my God. She just told me to chill. She just told me, do you know how impossible that, do I look like someone who can chill? All right, wait, okay,
No,
no.
not really. But me neither.
All right, I'm gonna go back to, wait, I'm just looking at the, oh my God. And now, see, now other people are in the direct. Shade means slandering. Let her shade you. Oh my God. Okay. So now there's other people in the direct chat. That is good. This is what we want. We want this to be less about me and more about you. Like for real, comma, yo. Like really. And okay. So this is good. So anyway, I do think you want, all right, I'm gonna get back because it's like, but really the more you can all do this, the better. And remember also, I live on the 4th floor. I'm there after 11 on Tuesdays, whatever. Come visit me. We'll do more of this. Yes, you're getting an A. Yeah, I think. Am I getting an A? That's a question. All right. So no, wait, but this all stealing. No, and you literally wait. Okay, I am gonna. There are people that have taken this class who never got an A on an exam, like who never got in the 90s on an exam, but totally partly because of this type of participation. Like, yes, the sense of humor, but you don't have to be funny to do. But this type of participation, even when it's not always exactly like math equations, like there are people that have gotten A's in this class without ever getting an A on the exam, and it's totally fair as far as I'm concerned because it's a class. Like, and there's millions of ways to do well in a class, and one of the ways is to make the class more of a class that other people want to come to and pay attention to, like for real. So anyway, oh, so this all started, this rant started because in the chat, what Charlene put, like no joke, the original thing that she put in the chat, and now a couple other people have echoed, she put what is in effect, her own words to what is in effect, form number 3. Well, I'll put in my word. Well, she said in the chat, does this mean we always need something to compare velocity to? And the answer is yes, that is true. And that is what this means in a big old way. Like the reason, well, I'll write it. I'll write it. Well, the reason this is called the principle of relativity is this is the moment in history that we come to realize that velocity is relative. It's always a relation. Well, I'll write it. I'll write it. Hmm. Okay. Okay, so I'll read the words in English first of all. What the words say, and if and again, I honestly I think this is what Charlene just said in the chat. It says velocity is always a relation between two objects. Velocity is never a property of just one object. It's always a comparison, is what this is saying. Now, you might even think, wait, didn't we just say that in Form 2? Well, yes and no. It depends. I mean, if you're that smart, if you're seeing, as Charlene did, in a way, yes, this is packed into Form 2, but it just popped out of Form 2, meaning this. Form 2, we said you can't do an experiment to find anything other than this. But this is 1632. People weren't doing experiments before 1632. When you've heard of the scientific method and why and Galileo is a hero that way and stuff like that, or you hear that like Aristotle was wrong because he thought wrong, he didn't understand velocity the way that Galileo did or something like Aristotle was a genius, okay? Like I mean all the people that came before Galileo were way smarter than I am and wrote a ton of things down and thought about a ton of things and made a ton of observations and like changed the world. What they didn't do were controlled experiments. That is like what Galileo added to the discussion. And that's a whole other discussion. But Galileo started this method for holding all factors as constant as possible at controlling the environment, controlling the circumstance, and then just tweaking one factor, one independent variable, slowly and progressively and carefully. Like he was the one that came up with this idea. Hang on a second, lots of things are going on whenever we're like making observations about the world. Why don't we like try to hold the world still, kind of? Like another quick example, really quick example, like this whole idea that you've heard, I think many of you have heard that like every kilogram falls at the same, sorry, that all objects fall at the same rate regardless of their weight. I mean, you've heard this before. I think like brick, that a 1 pound brick will fall to the ground at the same rate as a 10-pound brick. Like that's true. And that comes from Galileo. And like Aristotle did not think that was true. And blah blah blah. Now, how did Galileo come to like decide that? Well, partly it's because he was the first person to say, hang on, when things are falling, there's like a lot of factors going on. Like there's weight, but there's also volume and size and shape, and then air resistance and like all these things. So if we really want to ask the question, how does rate of fall depend on weight? Then what we got to do is create a situation where everything else is held like when all other things are equal except for the weight. What we got to do is just like take various objects that are the same in all other respects as much as we can and take them to the same height, right? And drop one after another, just changing the weight and seeing what impact that has on the fall time. Or right, this is just an example, but and let's do it over and over again, and let's do it in a way where I could write the instructions down and give to somebody else. So it's not even really about me anymore. It's about here's how you control variables so that you're just tweaking what, so that you're just tweaking. No, so that you're just like dialing one independent variable and seeing how nature responds in her manipulation of the dial for the dependent variable. Like, let's get it down to cause and effect, so to speak, or input and output, even better, right? Like that whole, and let's do it in a way that once we're done, we do it 50 more times, take all the data, and then turn around and say, here's the instruction manual. You do it now because otherwise it's all about even 50 times, it's all about me. So let's make it about you too, and you and you and you and the guy in China and the guy in Mesopotamia and the gal in Israel, etc. Right? That idea. I mean, that took centuries to develop. Like, whatever. That's Galileo. So Galileo's now doing experiments in his bedroom, in his office, in his study, whatever. He's doing experiments, and experiments are new. And experiments are a new way of gathering or verifying truth, right? Up until now, there's like philosophy, there's like thinking and writing and drawing and arguing, right? But it's like thought. And there's different branches of this thought. There's ethical philosophy, political philosophy, natural philosophy. So Galileo's doing natural philosophy. He's like thinking about the world just like Aristotle did and Plato did and all these people and Copernicus did, all the right. But now Galileo's saying, hang on, when we're thinking about when we're doing natural philosophy, I think we should develop this method called the scientific method, where we should be super careful about, like, if we're doing natural philosophy, it should be about collection of measurements called data, and it should be about collections in ways that are reproducible and controlled. And like that's how we should come to conclusions in the realm of natural philosophy. So now Galileo starts developing this experimental thing, this experimental method, the scientific method, right? Which now is starting to make natural philosophy into this thing that in modern terms we call science, or well, we call physics, and then we call science, right? Meaning it's a branch of thought that specifically is tethered to reproducible methods for collecting data, right? That is called, i.e., experiments. So that's like a new thing. And it's a new way. It's like a new Supreme Court of truth is the experimental court. So Galileo in form two says, yeah, okay, I've just like developed this idea called an experiment, like get with me on this. And then and some people do and some people don't. And a lot of people do as long as it's not threatening their whole worldview, right? It's like people like people like ChatGPT when it allows them to write papers, but they don't like it if it's now going to whatever, like take write a letter that takes money out of their bank account. You know what I'm saying, right? So people are like, oh, scientific method, that's cool. I don't see. I mean, say you want to like roll balls down inclined planes and like have pendulums in your office, we'll give you money for that. So Galileo says, okay, but if you're down with that, you can't, I'll tell you this, you're never going to come up with an experiment that's going to determine whether something's actually moving or not. And then he goes, and since we now all have just tacitly agreed that experiments are the arbiter of truth in the natural world, then I'm going to say what Charlene said, which is, and since no experiment can measure a solitary velocity, then I'm going to say there ain't no such thing as solitary velocity. That's the leap. That's the leap that Charlene made. I mean, it's not, I mean, it is a leap. We're saying we can't experimentally measure it. Therefore, it's meaningless from now on. Is it meaningless in raw philosophy? Is it meaningless in my head? Well, it's apparently not because we're talking about it. But is it meaningless from now on in physics? Yes. What we're saying is from now on, if we're going to pursue science, if we're going to study motion in the world of space and time in an experimental way, from here on in, whenever we use the word velocity, to us, it's a comparison. It's a relation between two objects. How fast is the Earth moving? Well, it is moving relative to the sun. It is not moving relative to itself. And then you say, well, okay, but which is the real? No, yeah. There is no real, I mean, there's reality. I'm not saying that, but which is more, from the perspective of the Earth is not moving, the sun is. From the perspective of the sun is not moving, the Earth is. Which perspective is actually scientifically correct? Well, as long as neither of them is accelerated, which actually they kind of are, so that, but but put that aside for later. What we're saying here is any perspective that is not, in fact, I'm going to write like, in other words, any reference frame, any perspective, any coordinate system, any object that is not accelerated is correct, is valid, is legit, is as legit as any other, is correct. That's what we're saying. So velocity is always a comparison. It is right. The Charlene point. I mean, you got it when she said it probably better than when I'm saying it. We are now saying, if you say, how fast is that thing going? And I say, compared to what? And you say, no, not compared to anything, just like how fast is that thing going? I say, no, like does not compute. Like that's not a question. And literally, and I will move on. I know I'm screaming and we have 20 minutes. Literally, what we're saying from now on is how fast, asking how fast something is like asking how taller is somebody. Like literally, you can say to me, how much taller is your sister than you? And I could answer that question, or I could even say, well, like -3 because she's shorter than I am. Like I could say she's not taller than I am, she's shorter than I am, or whatever, right? But if you literally say, how taller is your sister? And I'm like, wait, how taller? I mean, how taller is my sister? And you go, yeah, how taller is your sister? And I go, well, compared to whom? And then you go, no, not compared to anybody. Just how taller is he? I'd be like, dude, I don't even like understand this conversation anymore, right? Which might be, we're saying that's the way velocity is from now on. There is no conversation or measurement of velocity unless it's a relation, unless it's a comparison. And the reason for that, and the reason no one thought that until 1632, they might have sort of thought it just like you sort of thought it when you were 8 years old, I bet. But they didn't think it was like really a truth or like really a thing because they didn't really have experiments to really picture and think through how, oh, yeah, wait, when we think about the laws of motion, like they would play out a certain way in experiments. Experiments tell us the truth. If experiment can't tell us this thing, then this thing doesn't exist in that way. Like that's what we're saying. Okay, I'm going to pause. There's stuff in the chat, thank goodness. So are there more forms of this coming? Yes. Do any of them ever become like math equations? Yes. But are they coming today? No. This is where we stop for today. And I will look in the chat. But good, there's one message. Let it rip in the chat. Even if we end up having a 20-minute discussion, I'm fine because this is a lot. But this is the cornerstone of physics, is this idea. And every idea in physics, no matter how hard it seems or how detailed mathematically it seems, in some ways, I would argue, traces back to this. And this, in some ways, is totally obvious. I know you've all kind of thought this when you were 7, or if you ever liked physics, it might have sort of been because you sort of liked playing with this. But I'm telling you, it's real. It's not just a game. And I'm also telling you, notice every time we say one of these things, we're saying, unless something's accelerated, right? We're saying as long as something is constant speed or constant direction, then you can't feel the difference. You can't experiment the difference. You can't measure anything but a relation. Like as long as things are not accelerated, then everything is a matter of perspective. However, once things are accelerated, right? Once the airplane is turning left or turning right or hitting turbulence or speeding up or landing, like, right? Once velocities are changing, then things happen. Then it's a new game, which is why the next topic, of course, is acceleration, and why in a minute, after I look at the chat, we're going to seemingly shift gears and start doing the math problems of acceleration in homework 4, because acceleration is then when we can start actually nailing things down that seem a little bit more objective or a little bit less comparative. Okay, it's enough. Um, English word. Okay. English words. Right. English words. I think I get. Oh, English words. Yeah. Okay, I'm going to shift gears, but I'm also going to say again, and I'm not going to over dwell on it, but I really do. There were other people in the direct chat, even besides Charlene, but they didn't give me permission to use it, so I'm not. But I also just, and I don't want to make the whole thing about Charlene all the time, but I'm happy to as long as she. I mean, but I want to point out that it's not just that she said like good, like comprehend. Okay, I want to point out to all of you in general, saying physics correct physics things in chat is good, but also saying in the chat, like when you're having brain overload or when I've said too much about one thing, even if you've got it, that's like super helpful. And remember, that's one of the portals. One of the portals is please go back. Like I need you to say that again, or I need you to flip a page back. But another one of the portals, like for points, is please go forward, which doesn't have to mean go faster. It could just mean, wait, please move on. Like you've said too, like you're just saying too much about this already. And my brain just can't, it's totally helpful. Okay, so I'm going to move on. Um, so gear shift, and I know we have 20 minutes, a little bit less. Oh, okay. I'm so scared. And I love, and yes, okay, I'm down. I'm looking at the chat, comma, yo. And I see that there are people in the chat whose sense of humor is a little bit like mine, in that sometimes it's hard to tell. But yes, okay. But now I'm going to homework 4, average acceleration. No, but I do appreciate it. And I'd rather the jokes than I mean, even when I don't get whatever, you get the point. All right. Average acceleration. Okay, so I'm going to screen share. Okay, I'm going to screen share. Bear with me for a second. Okay. And now here's where we're going to start going like a little, I'm going to screen share, but I'm going to skip. Like if you had any issues with, well, all right, I'm going to screen share. Hold on. All right, so this is what we're talking about here, right? Right. Um, there's some warm-ups, reviews. I'm just going to like say the answers out loud right now so you can know whether you did it right or wrong. Again, if you're doing homework for me, you are showing the 5-step method, you are creating a self-sufficient document, all that stuff, and you're getting all the points eventually as long as you do all of those things. But I am not going to, like, I'm going to try to make, tracks here. So I'm just going to say the answers here. If you have any issue, let me know right now in chat or later on, email. But like, so for this first one, Berlin and Rome, you draw a diagram, all this stuff, total distance for the journey, 700 miles. Sorry, in my diagram, I would make a point of labeling north as either positive or negative. Okay, wait, I'm going to slow down for a second. This is just a warm up and it's just a practice. But now that we have Galileo's principle of relativity, part of what happens with us now, where this starts to become useful, is that every time you draw a diagram now in step 1 of a problem, part of what you should be doing is making your perspective or your coordinate system or your frame of reference, your reference frame, all ultimately the same idea. You want to be making that clear. like from what speed are you, from whose vantage point are you looking at this problem from? And let's even say more particularly, we're still in one dimension of space here. Our analysis, our homeworks, our problems are still in one dimension of space. So one thing you want to start making clear here is like, what are you calling positive and what are you calling negative? It's up to you. Galileo is saying you can choose your own coordinate system as long as it's not accelerated. But once you choose it, you got to stick with it and you got to make it clear. So I might draw a little I would draw a little diagram here where like I would put an arrow pointing north and label it as positive. And I put an arrow among other things. And like I would have an arrow going south and I would label it negative. Could you do the reverse? You could. And then just your answers would have to be consistent with that. But okay, I'm going to call north positive and I'm going to call south negative. Therefore, total distance I'm saying is 700 miles. Total displacement, since she flies from Berlin to Rome, the total displacement is negative 700, right? If I label things that way, from Berlin to Rome, because Berlin is north of, yeah. So answer 700 miles, negative 700 miles. What's our average speed for the journey? 700 divided by 4, which is like 175 miles per hour, right? And what's the average velocity for the journey? Negative 175 miles per hour. Negative because it's south. Those are the, I'm just looking at the chat because something just happened in the chat. It might actually be an issue. Okay, different person in the chat wrote, Galileo really said, have free will, comma, yo. No, they didn't write comma, yo, but right. And that is funny. And that and it's such a good, it shows that that person's listening to me and it is a different person. It shows that that person is listening. If you're getting the message from all my yelling that like Galileo is saying have free will, now I'm going to be more specific though. What Galileo's really saying is have free will when it comes to constant velocities. Like for real. Like we're not saying everything is a free for all. We're not saying everything in science is just like a matter of how you want to look at it. Then it wouldn't be science, right? But we are saying that velocity is a matter of how you look at it. So some other things must not be. And in a way, acceleration is one of those other things. So there's free will if you like. I mean, I know it was a joke and it's a cute, like it's a helpful joke, but like there's free will if you like when it comes to constant velocities, but not so much when it comes to acceleration. Hence why we're like moving along in the course. Okay, but good joke. I like it. I like, oh, yeah, ooh, I'm just gonna say another different person in the direct chat. You got, and it's rocking my world. When I see these comments, like even if they're jokes, these jokes, first of all, I think are funny. But second of all, like you couldn't be making them unless you were like actually with me, like curricularly. So thank you. And someone just wrote, being a comedian about science is my specialty. They meant themselves, not me. Good. You can't be funny about science unless you get science. So rocket, comma, yo. All right, but I'm gonna go. So and the more people are doing this, the more people I know are in the class. It's like 3 people just did that. So thank you. And you should all submit for points. Okay, I'm gonna move on. All right, so my answers, I hope the answers were clear. If there's not, put it in the chat. Then the next question, instantaneous velocity. Now, this, you watched videos about this of me, but we haven't talked about it as a group. Instantaneous velocity. In fact, there's like a whole equation for it, which I'm not going to rabbit hole right now. Remember, instantaneous velocity is average velocity taken to the limit as the time interval gets arbitrarily close to zero, right? Gets closer and closer to zero. Instantaneous velocity is the limit of average velocity, right? And that, so you can write it equationally. And what that really means from a calculus perspective is instantaneous velocity is the derivative of position with respect to time, right? That's what instantaneous velocity is. It's not how fast you were going on average between here and there. It's how fast you were going here, which really doesn't make sense as a concept at all in half of our brain unless we sort of are familiar with and used to and sort of comfortable with the idea of limits and derivatives. Right? That's what instantaneous. So instantaneous velocity is like how fast you are going at an instant, or really how fast you're going in the limit as the time interval approaches a instant. And we always have to say it that way. Because if it were literally just literally an instant, if it were literally just like how fast are you going in a frame of a movie, like if it were literally just how fast you're going in a photograph, the answer would be not at all fast, right? Because it's a photograph, like, right? But yet, if you take a photograph of something, if you extract a frame from a larger set of frames that we call a movie, a film, right? Then we know at any one, if you say that at every one of those frames there's no motion, then all of the no motions would add up together to make a total of no motion. And yet we know in a movie there's motion. So in each one, in the limit, something must be happening. Right? And that's why it's not at time equals zero. It's as close as we can get to zero without actually being zero. And that's this mathematical concept called a limit, or ultimately called a derivative. So anyway, so now we get to that in number two. And like that's a very hard concept in a way, but the key lesson to the concept is you always use context to figure out the limit. So in this case, it's just trying to demonstrate that it's all about context. So it says a car travels at constant velocity for 30 minutes. During that 30 minutes, it travels 40 miles. What's the car's instantaneous velocity at precisely the 18th minute, 42nd second? It's saying all that just kind of to intimidate. You'd kind of like to be like, whoa, but do I know 18th minute, 42nd second? But what the answer is, or how you do, like the answer is, well, the way you do it, I'm just saying it because I'm trying not to rabbit hole, even though I'm totally rabbit holing. What you do is you say, well, I don't know. I don't know how it's going at a moment, but I know on average for this 30 minutes, on average, it must be traveling 80 miles per hour. Where'd I get 80? Because it travels 40 miles in 30 minutes. It travels 40 miles in a half hour. So on average, between the beginning and the end, on average, it's traveling 80 miles per hour. Now, that in itself is average velocity. That does not tell me what it's doing at any given moment. For all I know, if that's all the information I had, it could be going fast at the beginning and then slow and then stop for a while and then reverse, right? All I know when I divide 40 by one half and get 80, all I know is its average velocity is 80 miles per hour. But then it also says that it's traveling at constant velocity. So that's the key piece of context there. It's saying if I were to look at the graph is a horizontal line. It's saying you know the average and you know here's how the average is changing. Here's the trend in it. The trend is it's not changing at all. So then it is fair to put those two pieces of information together and say, oh, fine. Then at the 18th minute, 42nd second, it's doing the same thing it's doing at the 18th minute, 43rd second, which is it's going 80 miles per hour. So I'm going to move on. But I'm saying the answer to that one, to Roman numeral number two, the one in the middle of the screen right now, the answer is 80 miles per hour. But be careful. The answer is 80 because of two facts. One, three, the displacement, the time, and the fact that we were told that this thing was going at constant velocity. So right, you couldn't have said 80 without incorporating that piece of information. So the lesson is you can figure out a dot on a graph as long as you have enough information about the whole graph. But you really need to know the whole graph. You can't. Okay, I'm moving on. I think you get. But if you don't, like, tell me. I'm moving on. So the answer is 80 for that one. All right, now we have 6 minutes left. Hold on, let me just. You know what? Because I'm just trying to like make some progress with us all. Well, uh, for the moment, remind me tomorrow if you can. I'm going to skip. Well, no, fine, three. I'll say it sort of quickly. But again, stop me. I'm just trying to but stop me if when you want. But in number three, now we're getting it. Okay, fine. So average acceleration is change in velocity per change in time. In other words, V minus. I don't want to switch boards. It's the thing that's at the front of the board, the PDF today. A bar, triple equal sign, V minus V naught over T. Please notice it is not a coincidence. This is kind of like our second useful, directly useful equation. We also had that limiting thing, but that's like important, but it's not like directly useful. This equation looks a lot like the one big equation we've had for a month. What we already know is V bar triple equal sign X minus X naught over T. Now I'm saying A bar triple equal sign V minus V naught over T. If you write them down next to each other or stare at them, you will see that they look very similar. That is not a coincidence. We're saying it's the same relationship. Just as average velocity is the difference between two positions per time, average acceleration is the difference between two velocities per time. But notice there's a bar on the left side of each one of these equations. There's no bars on the right side of the equation. It ain't jail. They're like truly, right? With the left side, we're saying an average equals like a change in this coordinate per change in that coordinate. So I'm saying A bar triple equal sign V minus V naught over T. It means that acceleration from here on in is the change in velocity per time, not the change in average velocities, the change in instantaneous velocities. Velocity here at this point in time and space versus velocity there at that point in time and space. Like that's why we needed to sort of define that concept before we could define this concept. So average acceleration is so average. Okay, please write this down if you're still, we've got 3 minutes. I don't know if you still, when you were like in eighth grade, I don't know if they still do like Miller's analogies, like on SAT. You hate it, but you know, like analogies, like write down like average velocity colon position colon. When I say colon, I mean those two dots, like the vertical dot, right? Average velocity colon position colon average acceleration colon instantaneous velocity. I'll say it again in English. What I'm trying to say is average velocity is to position as average acceleration is to instantaneous velocity. It's a direct analogy and it's not a coincidence. Bottom line, final thing, I know with 3 minutes left, if you sort of kind of maybe understand that instantaneous velocity is the derivative, it is the first derivative of position with respect to time, then acceleration is the derivative of that, right? Velocity is the derivative of position with respect to time. Accelerate, meaning it's the change, right? Acceleration is the derivative of velocity with respect to time. So acceleration is the derivative of position with respect to time. Acceleration is the second derivative of position with respect to time. Okay, that's like the summary of the concept. So with 2 minutes left, part A of problem 3, expressed in miles per hour per minute, the average acceleration of my Toyota is 60 miles, is 30 miles per hour per minute. Like that is the answer to A. 30 miles per hour per minute. And you might think that like your high school teacher might not like that way of saying it. And maybe sometimes neither do I. But it is a correct, valid way of saying it. And in fact, I think it really gets the concept across. What that means, I'm going to say one more time. I know we have 1 minute and I'm going to like stop here. When I say the acceleration is 30 miles per hour per minute, that means literally that. It means every minute the speed will change, will increase by 30 miles per hour. There's 2 references to time because velocity already has a reference to time in it. And now we're measuring that change in time. So there have to be 2 references to time. And there's no rule that they both have to be the same type of time. I mean, ultimately it's easier, which hence part B, which we'll do tomorrow. But when you're picturing accelerations, I think it's much easier to picture them this way. What's the rate? Every minute the car gains 30 miles per hour of speed. That's the concept of acceleration. And then you have to do unit conversions to get a much smaller, crazier number in miles per second, or what we call miles per second squared. We'll do that. And I think it's like, I think the answer ends up being, but don't quote me on that. It's like, I think 3 point something something times 10 to the negative fourth meters per second squared. It's like a really small number. It's something times 10 to the negative fourth. It's either 3 point or 1 point, but don't quote me on that. It doesn't matter. But if you got 10 to the negative fourth, I think you know what you're doing. And it's 12:05. So I'll see you. So I'll see you in 2 days. And thank you all for the participation, really. And I'll stop this. Oh, chat. Yes, goodbye. Awesome. Oh, wait. I'm looking and I will answer questions for a second. Hold on. I'm stopping the recording and I'm stopping the madness.